So, is the presentation visible? Okay, so today we'll start with, welcome to the course Basics of Materials Engineering. So today's course, and we have topic Imperfections in Solids. So this is your course that is taught by Professor Ratna Kumar and from Department of Mechanical Engineering, IIT Madras, and I'm your TA, Alka Jangid from IIT Kanpur. So firstly, we'll be going through some sample assignment questions. Then we'll be going through some notes which will help you to solve the assignment questions of the present week. So first question is, what is the stacking sequence in the FCC crystal system? So if you don't understand any questions, so please you can ask yourself, you can unmute and ask. So first question is, what is the stacking sequence in the FCC crystal system? So your options are AAA, ABAB, or ABC, or ABCD. So these are different stacking sequences found in different crystal systems. So for FCC, your answer will be ABC, ABC. Now from here you can see that in case of HCP, if you okay, so along the close back direction, if you go in this direction, you see that for a particular plane, you have the atomic positions in this way. Then another plane is B type. Then the atomic position repeats at the third one. So it is AB type of structure for HCP. In case of FCC, when you go along 111 direction, you see that AB, this atomic positions, it repeats after two planes. So it is ABC type of structure, and both they have packing fraction of 74.74. Now second question is, what will be equilibrium vacancy concentration?
Madam,
Yes.
I do have doubt in that first question.
Okay.
I have understood for this HCP system, but
Yeah.
how how it's ABC for FCC?
ABC for it is
FCC.
it is for FCC in case you when you take along one direction, in that case your atoms will look like this. So at a plane, then again AB, this type of structure, then C plane will be there, then it will repeat. So for example, I think I should have FCC. One second, let me check. Okay, so from here you can see this one, right? In this one,
Yeah.
so when you'll be going through face this body diagonal, if you will be taking along the body diagonal, then this atom will be having a plane in this direction, then three atoms will be having a different type of these atoms, and these like these one with these one, and this one with different one. So according when you'll be coming up to the this other body diagonal, this will repeat only, and between them there will be two different planes in this sequence which you saw here in this sequence.
It's not much clear, but like in FCC,
Hmm.
the below four atoms, if you consider it A, and
Yeah,
all the face atoms, if you consider it B, then
yeah.
again the third come will A only, about top atoms.
No, they will be having differently. They will be having in this manner. Like these are not similar. Like this one, see, pointer. This one is in this manner. So this point will be, this void will be filled like that. In this case, it won't be filled. Like when you'll be seeing this, these two aren't same. B and C.
Okay. So this two face atom will come under B and two face atom will come under C. It's like that.
Which ones? Face centers
In
your,
FCC,
yeah.
yeah, in FCC,
Hmm.
below four atom will come under A. Then
Yeah, these
then
are
after in
A,
B,
B, yeah, B are different. B will be like taking some this one triangle will be following this one, then remaining voids will be filled by these C atoms. It will be different than this one. So you
but
won't be
number of
able,
atoms in B and C will be two.
B and C will be,
Two in case of FCC.
yeah. In FCC 2, what do you mean?
Like in if we are considering B, then
Hmm.
under the B section, two atoms will come, and under the C section, two atoms will come. Is it like that?
I'm not getting what you're telling. Like these these won't be similar. Like what uh, the holes that are the gaps that are here, that B part will be covering, C will be covering differently. In this case, it is repeating as it is in case of HCP.
Okay.
Yeah. From this picture it is not very clear, but in FCC when you have atoms nicely packed, then you can understand better, I think. Here you are not able to understand like how it will be ABC. Okay, so next question is what will be equilibrium vacancy concentration in aluminium at 0 degree Celsius if HF upon T melting is 8 multiplied by 10 to the power minus 4 electron volt per Kelvin. Now your answer, firstly you have HF upon T melt. So T melt you should know for aluminium it is 660 degrees Celsius. So you can convert it into Kelvin. Then using that you can calculate HF. So you'll be getting HF 0.746 electron volt. Now for the other, the formula will be xv equals to 10 times the exponential of minus delta hf upon kVt. Here HF is your enthalpy of vacancy formation for a single vacancy formation, and Kb is Boltzmann constant. So you should remember its value for certain numericals if you are given, and temperature is 273 Kelvin, 0 degree Celsius. Now keeping all these values in the formula, you can calculate it will be around 1.68 times the multiplied by 10 to the power minus 13. Now question 3, the number of atoms centered on the 110 direction for the FCC structure is, your options are 1, 2 and 3 and 0.5. Now in case of FCC, your 110 direction will be along the face diagonal, and the answer will be 2. So from this face diagonal, when you will be taking this, so we can see that one atom which is at the corner will be half. So half will be counting that, then middle one will be entirely on this line. So it will be 1 and 0.5 will be from another corner. So 2 atoms will be on the direction 110. For different directions also you can calculate. So if it is, for example, if it is 100, in that case it will be only 1. Now the presence of vacant lattice sites in a crystal. Your options are decreases its entropy, increases its entropy, has no effect on the entropy. So vacancies are, we know that it is a point defect and these are always found in any crystal. So what vacancies do, they'll be reducing the energy of the system, plus it will be increasing its entropy. Now how the entropy part works is that first is configurational part. So for example, this is a lattice. If there would be one of the atoms would be here as well, then in that case there will be only one configuration possible for this one. So there won't be many configurations possible, just one. And if there is only one vacancy allowed to exist, then there are multiple configuration possible in this case. So configuration, there will be arising some entropy. Other part will be due to vibrational entropy. So atoms adjacent to a vacancy, so these atoms, they are less restrained than those that are completely surrounded by the atoms, and thus they can vibrate more randomly. Each vacancy contributes a small amount of vibrational entropy to the total entropy of the crystal. So these atoms will be vibrating at higher compared to the ones that are completely packed with other atoms. So it will be increasing its entropy. Next question is, what is the terminology representing the movement of block of atoms along certain crystallographic plane and directions? So options are glide, slip, twinning and jog. So there is movement of block of atoms. So block of atoms can be also defined as dislocations. So dislocation movement is defined as slip. So your answer will be slip. So slip is a mechanism of plastic deformation along with twinning and clamping. In slip, half planes of atoms or block of atoms are known as dislocations. They move on slip planes in slip directions. And while in the twinning, reorientation of atoms occurs, which can be in a fraction of atomic distance also. So it necessarily need not to be a multiple of a atomic distance. And jogs are developed by the interaction of dislocations. So these are the what that make barriers for the dislocation movement. So this is not terminology that is used for movement of block of atoms. Sixth question is, which of the following is a point imperfection Your options are vacancy, interstitial C, Frankel imperfection, or Schottky imperfection. Now these all four are point defects, so these all will be the answer. So in case of vacancy defect, we can define it as an empty site, empty atomic site in crystal. Interstitial C will be when atom occupies an interstitial site, so it will go and occupy an interstitial defect, and that will be interstitial C. In case of Frankel, there will be a formation of vacancy interstitial pair. And in case of Schottky, a pair of missing anions and cations from the lattice, and these all four are point defects. Seventh question is, which one of the following defect is Schottky defect? So Schottky defect, as I told earlier, it is a pair of missing anion and cations. So out of these four, vacancy defect, compositional defect, interstitial defect, and surface defect, what it it will be in category of vacancy defect, because there is a pair missing of both anions and cations. And compositional defect can be defined as this is due to alloying or impurity present, so there will be change in composition of element. So examples are substitutional and interstitial defects. Interstitial defect, it is an atom other than the parent atom is present in the interstitial site. Interstitial site will be your voids between the atoms in a crystal. So other is surface defect. It is the outermost planes of a material that are surface defects, which is a physical boundary of the material. Question 8 is, calculate the packing fraction for BCC. And your options are 0.52, 0.68, 0.74 and 0.42. Answer will be 0.68. Now we can calculate packing fraction by number of atoms per unit cell times the volume of one atom divided volume of the entire unit cell. So unit cell, what will it is cubic, so A cube will be volume of unit cell. Now for number of atoms per unit cell, I told it in previous class as well, so it can be calculated by 1/8 times 8. So 8 is corresponds to 8 corners of the unit cell. So on all 8 corners there is an atom sitting, and atom is shared with 8 other unit cells. So 1/8 times 8 will be plus 1. 1 will be at the body center of the unit cell, which won't be shared with other unit cells. So there will be 2 atoms per unit cell in case of BCC structure. Now putting this value in this formula, so 2 will be number of atoms, volume of one atom will be, we can consider it as sphere. So 4/3 times the pi r cube divided by a cube. Now a and r, they have relation in case of BCC, which is shown in this figure as well from here. So it will be, instead of a we can put 4/√3 r. So r and r will be cancelled out and we'll be getting a fraction which will be 0.68. 0.52 is for simple cubic and 0.74 is for HCP and FCC crystal structure. Now which one of the following is an example of Frankel defect? Your options are one chlorine vacancy and one sodium vacancy in NaCl, one zinc vacancy and one zinc interstitial in zinc oxide, potassium at the sodium site in NaCl, or none of the options. So your answer will be second one, because as I told earlier, in case of Frankel there will be a vacancy interstitial pair missing. Now there will be a pair of vacancy and interstitial. So Frankel defect can be defined as the formation of vacancy interstitial pair In it, cation leaves its lattice site and sits in the interstitial site. In case of chlorine vacancy and sodium vacancy, in this case it will be a Schottky defect because there are a pair of vacancy. In case of this one, K at a sodium site in NaCl, it is an again example of Schottky defect. Now 10th question is Luder's lines are associated with. Your options are local plastic deformation under tensile stress, elastic zone, high hardness surface, or high toughness region. The answer will be local plastic deformation. So these are the lines that form when we perform tensile test on a specimen, dog bone sample. So these are the bands that form. These are due to local plastic deformation. So in these local regions there will be a plastic deformation compared to these areas. So these lines form during yield point phenomena, and it is a process of formation of slip bands during tensile testing, and it is local plastic deformation. Okay, so these are the bands that will be forming. Uh, I think Suresh has asked or someone has asked. So these are the lines that will be forming. These are known as these Luder's lines. Now these are in case of steels, there will be a localized because of yield point phenomena. There will be formation of these lines. Now moving on to notes based on these this week's assignments. So do you have any query in the questions? If not, we'll move on to the notes so that you can understand better what you can easily solve your assignment questions. Okay, so firstly, for the understanding origin of material properties, we require study at the atomic level. So there will be formation of interatomic bonds. So these will be holding atoms together. So these bonds are considered spring-like to understand the equilibrium positions of these atoms. Now there will be some atomic packing inside crystals. So this is also significant. Now these number of these bonds and their angles, these all define the material properties. These are the type of bonds that you have already studied, I think, and these are primary bonds and secondary bonds. First one, these are relatively strong and these materials melt between 1000 to 4000 Kelvin. So they can be covalent, ionic and metallic, and depending on these bonding, there will be various properties of these materials. Secondary bonding will be these are relatively weak and these materials melt between 100 to 500 Kelvin. Now these can be of van der Waals bonding and hydrogen bonding. Now these are various materials and their type of bonding and what type of properties that come because of these bonding. Now in case of ceramics, we have ionic and covalent bonding. Now in this case, these have very high bond energy. So this leads to their high melting temperatures. As we know that we use ceramics in case of material for making refractories and bricks and all. So these have very high melting temperature. And these also have large elastic modulus. And these have very small alpha. Alpha is what? Your thermal expansion coefficient. So these won't expand much when they are heated. Other is metals. In case of metals, they'll be having metallic bonding. So these have variable bond energy and they have moderate melting temperature, moderate elastic modulus and moderate thermal expansion coefficient. In case of polymers, they have two type of bonding. Along the chain, they have covalent bonding, and between the chains, they'll be having secondary bonding. Okay, so in case of polymers, these two type of bonding will be there. So these, the properties that they have directional properties because of presence of covalent bonding. And secondary bonding will be dominating because it is between chains, so it will be giving it small melting temperature, small elastic modulus, and small thermal expansion coefficient. Now, from moving on to crystal to the imperfection part, so last class we read what are the types of various crystals, but when we see for materials in our surrounding, then we see that they all have some imperfections. So there's no such thing called perfect, and materials and human society are alike, and they both work despite having defects. So many times perfection is not sought by nature, and defects in materials they lead to many good things too. For example, most of the metals are alloys giving desired properties. So alloying leads to enhancement in strength and various properties. So it requires presence of defects. And semiconductors also, they require doping, which is type of defect. Now, in case of semiconductors, you may have N type and P type of the doping. So, I think you have already studied these in your earlier classes. So, in this case, we'll be adding SP. So, it will be giving donor impurity contributes free electrons. So, there'll be one extra electron. So, it will be a donor type. So, these extra electrons will be conducting the electricity, while in case of boron, then it will be acceptor type of, so there will be formation of a hole. So these holes will be providing electricity conductivity. Now there are other advantages of defects as well. So as I told earlier, alloying and semiconductors, so there is also a metal deformation. So deformation of metals requires formation of dislocations and vacancies. These all are defects which are required for making sheets, wires, etc. using sheet metal formation, wire drawing, etc. Composite formation. So for increasing stiffness of metals, we also form composites. And strengthening, in case some strengthening mechanisms such as formation of precipitation, solid solution strengthening, dislocation strengthening, these all require formation of defects. Electronic devices which use semiconductors using doping, which is also again advantage of defect. And in case of steels, there are certain processes that are used such as carburizing, nitriding, and other heat treatments. So these all also depend on diffusion and formation of vacancies and other defects. Now, classification of defects. So any deviation from a crystal's completely ordered arrangement of constituent particles is called a defect or imperfection. And properties of material are influenced by the presence of imperfection. And mechanical properties of pure metal, they change significantly when metals are alloyed. Now classification, we can classify in depending on their dimensions. For example, zero dimension defect. In this case, your defect will be of the order of zero dimension. So for zero dimension, there will be atomic point defect, this will be in angstroms. And when the in case of line defect, which is 2D defect, oh sorry, it will be 1D defect line. So linear defects will be edge dislocation, screw dislocation, and mixed dislocation. And point defects will be vacancy, interstitial, substitutional, Frankel defect, and Schottky defect. In case of 2D, it will be planar defect. So these will be grain boundaries, twin boundaries, and free surface. In case of 3D, it will be voids and cracks. Now this is the length scale corresponding to various defects. So in case of line defects, it will be in micrometer of range. In case of volume defect, someone else has joined. Please mute yourself. Okay, so these are the dimensions of various defects. For volume defects, it will be 3D. So it will be of centimeters in the size. It can be, and for interfacial defects, it also has different range. Now moving on to point defects. So vacancies are lattice sites where an atom would have been present in a perfect crystal. For example, it is shown here. Okay, so here it is shown. So one atom is missing from this site and it is vacancy. Now this atom, other atom going into interstitial void part of the crystal, so then it will be interstitial type of defect. Now an additional atom exists at interstitial site, and there can be a pair of vacancy and interstitial in proximity, then it will be called Frankel pair. Frankel pair and Schottky will be mainly in your ionic solids or ceramics. So in ceramics there will be two, here it is shown Frankel pair. So your cation and anion, the pair will be, there will be a formation of it will be going into interstitial, leaving the exact position. In case of Schottky defect, your both anion and cation will be missing. Now in case of substitutional defect, a foreign element of larger or smaller size at a regular atomic position. So instead of this type of metal atom, there will be a different type of atom present at the regular site. Now vacancy defect, when an atom is missing from its regular lattice site, it is called a vacancy. Now it is impossible to create material free from vacancy defect because it reduces the Gibbs free energy of the crystal. Now the presence of vacancies increases the entropy and disorder in the crystal, and it decreases the density of the substance. Because there is an empty site, so here it won't be contributing to the mass of your entire material, so it will be reducing density. The concentration of vacancies increases with increasing temperature. From this equation you can see with increasing temperature there will be increase in vacancy number, and if we decrease the activation energy QV, the energy required for formation of vacancy, so this energy, if it is decreasing, then vacancy will increase. This is the equilibrium vacancy concentration equation. And now equilibrium vacancy concentration. So why do crystals create vacancies? It is a consequence of the competition between probability and energy. So there will be increase in entropy and reduction in energy. So these two compete and make these vacancies equilibrium. Now we assume that crystal is in equilibrium with vacuum, so there will be relocation of an atom from its lattice site to external surface, which will create a local distortion, increasing the internal energy called vacancy formation energy. So this energy is required, and the complete segregation of atoms in vacuum is not possible. Now competition between EF and the probability determines the equilibrium vacancy concentration. Now another topic is theoretical shear strength. Now for this you need to assume this is the your crystal. So now this is a plane of atoms, and this is another plane. Now interplanar spacing is A and interatomic distance is B. Now using this, now as you move on from, someone else has joined. Okay. So from here to here, when it will be moving here, so shear stress will be going from 0 to again 0 when this atom goes from here to here. So this will be a sine equation. So tau will be k sine 2 pi x upon p. Now this, along with this, it is an elastic displacement. So from elastic Hooke's law, you can say that stress is equals to your constant, elastic constant, times the strain. So your strain will be x upon a, g will be shear modulus, and tau will be shear stress. Now when you'll be equating both of these equations, you'll be getting value of k, and putting this value of k in this equation, you'll be getting tau max equal to gb. Here sine 2 pi x upon b, this part you'll be keeping 1, then tau max will be gb upon 2 pi a. Now b and a both are of the similar, when they are kept similar, b equal to a for simple cubic system, then you'll be getting tau equal to g upon 2 pi. Now here for an FCC material, the lattice constant A0, constant A and B may be related. Now for FCC it will be different. So you can calculate D based on A0, and then you'll be putting the value, then it will be G upon 5.1. And for simple cubic it will be different, it will be G upon 2 pi. Now for different elements it is calculated your tau max and your G. So we see that there will be difference. So theoretical strength is few orders of magnitude larger than the actual strength. Now why there is so much difference? It is because of the presence of defects. For example, in this case when we are assuming that these are two different lines of atoms. Now if this plane is moving along this direction, then all the bonds of the atoms, they are breaking, and there will be again formation of another bonds. Now to break those bonds we require a lot of energy. In this here when we calculated this, then we assumed that all bonds will be breaking. But in real crystal, there will be presence of vacancies, there will be presence of dislocations. So those help a lot when this crystal will be moving in this direction. So for example, if one atom moved, there will be formation of one dislocation. Now that dislocation will be helping in the movement of this plane. So that's why in reality the strength of material is very less. Now effect of point defects. So intrinsic point defects exist.
I have a doubt.
Yes.
Yes. Like, where can we use this theoretical shear strength?
Where can we use this?
Yeah.
Theoretical strength, you can't use it. Like you have just calculated if for a perfect crystal. If it is a perfect crystal,
Yeah,
there
that,
won't be any formation of dislocation. Then you'll be getting this order of strength. If you don't
yeah,
have,
that's why I asked. That
yeah.
like what will be the benefit of calculating if such material is not
So in case of at smaller level, smaller scale, like in case in microns or some sizes, we can form pure crystals. Okay. So in that case, you can see that it will be near to this, but still less than that. Your strength of
sorry,
that
but in which
crystals as
case,
well. Pure crystals,
and,
which won't be
how
having
can we
any
form?
dislocations and defects and impurities in that case, known as whiskers.
Okay. And like how can we find actual theoretical shears then of any material?
Sheer sheer strength of what?
Actual material
Actual we
which
can
have
measure.
some defects.
Actual we can measure. For example, how we measure tensile strength by plotting the curve. In that case, you can perform
Okay, so
shear.
only
Yeah,
by only testing we can.
yeah. We can actual strength, shear strength, we can measure by testing.
So there isn't any way to calculate it by considering defects. We have to directly test the
Yeah,
material.
because we don't know how many, like, either you have to simulate and consider all the dislocations that are present there, all the impurities that are present, or you can direct easily just test it.
Yeah. So is there any way to identify how much vacancy or how much defects are present in any material?
Defects based on density, actual density anomaly is there. Based on that, you can get what is the percentage of the material that is absent, but you can tell whether it is in form of vacancy or whether it is in form of dislocation. For example, you can
We
use
can't tell that.
TEM, yeah, transmission electron microscopy. By that you can tell how much dislocation are present in your thin material, but for that you have a lot of restrictions, like your material should be very thin plate, so like that. So for exact material, if you have like randomly sitting beside you, then you can tell it. Okay.
Yeah.
Okay, so effect of point defects. So how to generate point defects in a material? So you can either quench the material, you can plastically deform, or you can irradiate it. So these are various methods to generate defects. Now, first method is rapid cooling from melting point. Then more defects will be retaining at the room temperature. Now what happens? So at higher temperature, as we showed earlier, at higher temperatures more vacancies will be there as we keep on increasing the temperature. Now those vacancies will get freeze in that system when we quench it, when we rapidly cool it to the room temperature. So by that method, or we can plastically deform material, which will lead to formation of vacancies as well as your dislocations. So this is another. And we can also use irradiation, so that you'll be bombarding it with gamma rays or any other rays, then it might lead to formation of vacancies, interstitial C, and other type of defects. It is known as
And I
radiation.
have
Yeah,
one more doubt.
yeah, go ahead.
Like, uh, if there is a no, like can interstitial site be filled by a parent atom?
Yeah, yeah, that is called interstitial C, I told earlier, right? Interstitial
So
C.
it can be filled by a parent atom or a non-parent atom, right?
Yeah, it can be both. Impurity atom can also be there, and your
Yeah.
Interstitial, see, I think I told earlier. Interstitial site. So, interstitial, an atom other than the parent atom can be present, then it will be interstitial defect. And if the parent atom is present, then it will be interstitial C defect. So, this interstitial C defect requires a lot of energy, so it can only occur in case of irradiation when you are providing a lot of energy to the system.
So interstitial C and interstitial defect both are different.
Yeah, both are different. Interstitial meaning
Yeah.
other atoms. For example, in steel, what happens? Your carbon is present in iron atoms. Iron atoms
Yeah.
have certain voids, so in that your carbon atom will go and sit. That is your interstitial defect. If an
Okay.
iron itself is going and sitting at the interstitial of itself, that will create a lot of lattice strain, so that requires a lot of energy, so that will be irradiation, will be using irradiation. I think it should have given here interstitial atoms. Yeah, here I think there must be some of the atoms which will be sitting inside its own interstitial void. Okay.
Yeah.
So, irradiation in solids, it leads to displaced electrons, which can lead to ionization. This part is not important in metals, and it can also be displaced atoms by elastic collision. And this is important in metals. There can be fission and thermal spikes as well. Now, neutron irradiation, in this case, there will be primary collisions transfer energy to the atomic system, and there will be displaces atom from a normal position to position between lattice sites. So this is your interstitial C. There will be defect creation by displacements, their migration and interactions. And if an atom receives energy greater than EE, which is effective displacement energy, it will be displaced at higher energy. Cascading might also occur. Now, displacement spike is an energetic atom displaces all atoms it encounters, and if an energy is less than EE, the energy is imparted to the chain of exchange collisions. Now, such efficiency is higher in close packed directions, and vacancies generated due to irradiation often coalesce and form voids. Now, these are various type of effects that can occur if we subject our material to radiation. Now, formation of Frankel pair, exchange of collisions, dynamic propagation. So, if this is a, for example, this is your close pack direction, then in this direction there will be more of the accumulation of these defects. Primary knockoff. So, this, for example, this neutron is coming and it will be knocking off your atom from its original position, and there can be lattice vacancy, energy transport by focusing collision. So these all might occur. Now, the voids created by radiation damage, they act as obstacle for dislocation motion, so it leads to hardening of metal. So certain metals, they might undergo this type of hardening, making them brittle. So not all materials can be used for example, for making shields for radiation. And displacement spike might destroy order in alloys, and at low temperatures irradiation results in joining of vacancies. Someone has joined. Okay, so at low temperatures, irradiation results in joining of vacancies and interstitials surrounded by dislocations which impede dislocation motion. So strength increases but ductility decreases as shown here. And at high temperatures, vacancy coalesce and form voids, resulting in undesirable dimensional instability. Now, this is the stress strain curve for irradiated and unirradiated zircon alloy. So, in case of unirradiated, we can see that it shows a lot of ductility. Ductility is what? Your deformation is occurring a lot. And here, in case of irradiated, your ductility has reduced and strength has improved. Now, one of the use of the point defects is in ion implantation. This is a technique where you will be using some ions that will be implanted into steel, and it will be reduce its wear of tools, so it will be providing wear resistance by an order of magnitude. It is also used for preparing semiconductor devices, altering the composition and structure of surfaces. It is used for modifying surface chemistry for better tribological application. So, bismuth, nickel, molybdenum, these ions may be used for implantation. Titanium and boron implantation on oil burner tips improved their erosion properties, and it is used for injecting mixture of fuel oil and air in boilers. This is a non-equilibrium process, so there won't be any limit for solubility. Now, some of the point defects that I told earlier, Frankel defect and Schottky defect, you get many questions based on these in your assignments. So, Frankel defect is just your uh, pair of your vacancy and interstitial pair. So, so there will be an ion that will be moving into interstitial. And in case of Schottky, there will be pair of vacancies that have opposite signs. So there will be cation and anion missing from their sites. These two defects are important in compounds such as ceramics and intermetallics. And in case of Schottky defects, it is due to equal number of cations and anions missing from the lattice sites, and the results in decrease in density of crystal because the atoms are reducing in the crystal. And this type of defect is found in highly ionic compounds with high coordination number, so NaCl, cesium chloride, AgBr, etc. And Frankel defect will be, it is due to missing of ions, usually cations, from the lattice sites, and they occupy the interstitial sites. So cations will be smaller in size, so they will go and sit in interstitial. It has no effect on the density of crystal because atom is just going and sitting in interstitial. So number of atoms will be similar in the crystal. This type of defect is found in crystals where the difference in the size of cations and anions is very large. So difference would be higher in Ag and Cl type of atoms. So examples are AgCl, AgBr and zinc sulfide. Impurities in solids. So pure metals consisting of only one type of atom isn't possible. So there are very sophisticated techniques that are used to even get purity level of 99.999%. So at this level there are still 10 to the power 22 to 10 to the power 23 impurity atoms in a cubic meter of material. So the most material metals are not highly pure and they are known as alloys. Now addition of impurity atom to a metal, it might form solid solution. Solid solution. So in this case you have two parts of the solid solution. One is solvent. So solvent is your host atom, element or compound that is present in greatest amount, which is also called solid host atom. Solute is your element or compound that is present in minor composition. So just a smaller number of atoms, that will be your solute. A solid solution is formed when solute atoms are added to the host material and the crystal structure is maintained, and impurity point defects are observed in a solid solutions. Now, depending on the size of the atoms, they can be either interstitial impurity atom or substitutional atoms. So, substitutional will be taking regular positions, and interstitial will be taking the inner positions between the atoms without changing the positions of the regular atoms. Now, for these solid solutions, the solubility of solute atoms depends on several factors. So, for formation of solid solution, you have four rules which are also known as Hume-Rothery rules. So, first is atomic size factor, where the difference in atomic radii between the two atom will be less than 15%. So atomic radii will be very closer to each other, and otherwise substantial lattice distortion will be there and formation of a new phase might occur. Crystal structure. For appreciable solid solubility, the crystal structure of both metal must be same. And electronegativity, it should be as close as possible, otherwise intermetallics will be formed. Valences, so metal will have more tendency to dissolve another metal of higher valency, all other factors being equal. So if these all factors satisfy, then this valency, if it is higher valency, then it will be dissolving more. Now one of the example is copper nickel system. These are completely soluble in each other at all proportions and substitutional solid solution. So in this case your nickel will be taking sites of copper in a copper lattice. Now copper atom radius is 0.128 nanometer and nickel is 0.125 nanometer. These two sit very close to each other, side by side at the periodic table. So they have very close atomic radius, and they both are FCC in nature, crystal structure, and electronegativity is 1.9 and 1.8, and their common valences is +1 and for nickel it is +2. Now this is their phase diagram. We'll be studying about phase diagrams in next chapters, last chapters. So here what is occurring is that it is in form of liquid. One second. So in this area it is in liquid form. Both copper and nickel is liquid. This is your phase field. Here your both phases are it is also liquid, also solid, some part solid, and here it is complete solid solution, your nickel copper solid solution. These are their melting points. For copper it is 1085 and for nickel it is 1455. Other examples are copper gold, gold silver, nickel palladium, lead tin, and tin bismuth. Now other type of solid solutions are interstitial. In this case, impurity atoms fill the voids or interstices among the host atoms. For metallic materials with very high packing factors, the interstitial space is very less. Atomic diameter of the interstitial atom should be much less compared to host atoms. So maximum allowable concentration of interstitial impurity is 10%. Now carbon forms an interstitial solid solution when added to the iron and iron carbon system. In this case, carbon forms an interstitial solid solution, and here atomic radius is very different. So for carbon it is 0.071 nanometer and for iron it is 0.124 nanometer, and maximum concentration of carbon in iron is about 2%, and interstitial site radius in PCC iron it is 0.036 nanometer, and for FCC iron it is 0.053 nanometer. So these, I don't know at this level you'll be understanding this part or not, but in FCC iron, when then iron will be converting into FCC at higher temperature, then it will be showing higher solubility because it has greater interstitial radius. This is the phase diagram of iron carbon. So in this part, up to this part, 2.14 part, there will be formation of steel up to 2.14% weight percent of carbon. After that there will be cast iron up to 6.7 weight percent. Now composition specification. So when there will be formation of substitutional or impurity interstitial type of solid solution, then these equations you'll be requiring to calculate. So composition or concentration, it is a relative content of a specific element or constituent in an alloy. Now they can be either mass percent or atom percent, two type of percentages that you can use to specify your alloy. Now weight percent, so here weight of a particular element relative to the total weight of alloy. So weight of, for example, one type of atom, for example it is copper, so copper's mass will be here, so divided by total mass, so m1 plus m2, so your copper and nickel both their mass multiplied by 100. Now this will be weight percent of copper in your alloy. Like that you can calculate. For C2 it will be C2 upon total mass. And number of, here it is atom percent. In this case you have to firstly moles of copper divided by total moles, mole of copper plus mole of nickel, like that. So for calculating moles you can do it by mass divided by atomic weight. So what is mass of, for example, nickel, divided by atomic weight which is given on your periodic table, that you have to divide, then you will be getting number of moles that are present in the alloy. Now that's all from the notes. If you have any query you can ask. I'll be again.
Is it possible
Yeah.
represent 0 0 plane? 0 0 0 plane.
0 0 0 plane.
Yeah, 0 0 0 crystallographic plane. In a
No, they
cubic
won't.
units.
How can you have 0 0 0 plane? It will be a point at the origin. You can only have like 0 0 1 1 0 0 type of plane. 0 0 0 can be plane. It will be just a point for the origin.
Yeah, because it should have intercept, right?
Yes, it should have intercept. It won't be having like infinity, infinity, infinity. You will be, when you will be taking reciprocals.
Then, like, if we have to represent this FCC, a single unit cell of FCC, in the form of ABC,
Yeah.
then how can we represent?
ABC in case of FCC. So from here only I can.
Just I have drawn the figure. You just tell me, is it fine? No.
Yeah, figure you have drawn. Let me see. NFCC. You can simply, I think you can simply search stacking in FCC, then you can see some images where you can easily, like from color coding, you can easily understand how it will be
Will it be?
ABC'd.
Hello.
Yeah,
Will it be like that?
1 second.
Is my feedback?
ABC. Yeah, it will be something like that. Yeah, C and C will be similar, but the other two will be different. BC in between. Yeah, yeah.
Then one more question is, if you want to represent this one,
This one will be like 100 like that. It won't be 00.
like what will be the indices for this plane?
This is not in this present current assignment, right? I can tell you that's answer. It's not in
Wait,
current assignment, right?
no, it is not.
No, it is not. Okay. Then on which okay, where it is cutting? Like on which axis it is cutting? Y,
So if
X.
this is x-axis, this is y-axis, and this is x.
Okay, so on Y, so it will be 010. Like on Y, it is cutting at, for Y, it is cutting at 0.
Here it is origin.
Yeah.
So will it be 0, 1 here? Because I was unable to understand this indices for this plane, and this plane as well.
So these all are 100 type of planes. So now you have to, in case of what, you have to figure out what is the intercept. For example, when it is cutting Y on 1, then it will be 010. If it is cutting Z on 1, then it will be 010. So I think
But
it's cutting Y in -1. So 01 bar 0, I think it will be 01 bar 0. You have to shift origin, I think, in this case. Yeah, you have to shift origin, so it will be 01 bar 0
to, for,
because it,
to find, yeah,
if you have, you would
intercept
have shifted it one plane
and
earlier, like at Y, if it is cutting on 1 and other two to the infinity, right? It won't
yeah,
cut X and that. Yeah, so it will be one. If it will be one plane after at Y, then it will be 010. So if it is there, so it is 01 bar 0, the first one that you showed.
yeah. If we shift origin here,
Yeah,
then
yeah.
So I have doubt in this X-ray diffraction method. Like I only understood that X-ray diffraction method is used to find that.
Is used to find.
It is used to find material composition.
Yes, phases,
But
whatever
how?
phases that are present. Or so in case of X-ray diffraction, what will happen, your diffraction of the your X-ray will be occurring. Okay, there's a lot of background noise. Okay, so in that case, so from Bragg's law you can, Bragg's law you understood.
No. Is it
So
Bragg's law?
yeah, so sir hasn't taught Bragg's law,
No,
is it
no.
so?
No. So week two, yeah.
Okay, so from Bragg's law, you can, like, you can relate your theta. Theta will be angle. So whatever angle is there, at an angle your X-ray will be coming, right? So with that, there will be some diffraction. Diffraction angle will be there, your theta, and relating to that, you can relate your interplanar distance. Interplanar distance we talked today also in shear, when we calculated your theoretical shear strength, right here. So interplanar distance and your theta will be having some relation. So depending on that, at particular distances there will be a high intensity peak will be present on your XRD graph. So at those particular angles, you can see that for that particular angle will be, theta will be different for all type of materials, elements that are present. So for example, if you have copper nickel system and you are performing XRD on that, so you'll be getting copper peaks and nickel peaks. So by that you can tell that this system has copper and nickel. So depending on if there is a different phase also present, so for that phase there'll be different type of peaks present, like that, like those peaks you can define. So from those peaks you can understand what type of phases that are present there in your material. Or depending on intensity you can also tell like how much material is there, how, what is the volume, and other things also you can determine.
Like from the magnitude of the peak, we can determine copper and nickel.
Yeah, depending on peak intensity doesn't help much, but depending on, like, for example, broadening can also be there, so that can help you with understanding what is the grain size, or what is the, like, strain that is present there from that. Or if the peaks are merging, then you can understand that there is formation of some substitutional alloy. So you can tell what type of phases are present also. Like if they are separately present, then there will be different peaks. Anything else?
Yeah, just one more.
Okay.
Yeah, it is about the triclinic structure, which Sir has taught us.
About
Hello.
triclinic structure.
Like previously, Sir has mentioned that we can consider any crystal only if it follows
Yeah.
rotational symmetry and translational symmetry both.
Yeah.
But they mentioned that triclinic structure doesn't follow any of them. Then how can we consider triclinic as a crystal? It is fully random, right?
1 second, I need to check whether, because most of crystals follows the symmetry, rotational symmetry at least. It is showing like triclinic crystal has no rotation of symmetry.
Yeah, that's right.
Did sir say like all crystal systems have to follow the rotational symmetry or the real ones, real crystals?
They told that like a structure is only qualified to be called as crystal if it follows rotational symmetry translation.
So it has like one fold, like you have to rotate entirely 360-degree to be to reach again.
But but as per my understanding, the triclinic structure is fully random, right?
Yeah, A, B, C, and alpha, beta, gamma, nothing is equal. So
So how can we consider it as a crystal?
you can repeat it and reach to the entire crystal system in that case as well. But yeah, what sir says, that is also like there should be some rotational symmetry to it. In that case, it doesn't have, then why is it a crystal? Why is it defined as a crystal? That part I need to study and I can tell it in next class, I think.
And
Anything else?
so last is like what is the relation between this crystallographic direction and the property of a metal?
Crystallographic direction
and the physical property of the material.
okay, so crystallographic direction, yeah, so slip directions you understand, right? Slip direction, slip planes.
No.
No?
Or until this point. Because,
Yeah, okay, so for example, currently you're seeing some, okay, in this slide for example, if you are moving in this direction or you are moving in different direction, for example, one second, let me use pointer. Okay, so in this direction and in this direction you have different type of atomic packing density, right?
yeah, yeah,
Yeah,
linear density. So,
yeah, so linear density is different. So if you are for example, if you're taking a crystal, single crystal for example, then you're deforming it in this direction and in this direction it will be different because it is close packed in this direction, then rolling of atoms will be simple in this case, right? If it is a fully packed direction, here as we talked in this direction rolling is easier because there is less depth it has to go. If we are, for example, if there would be a different direction where these would be separated to the more distance in 100 direction, right? In that case you have to apply more stress to deform it. So mechanical properties, for example, if you are using uh, tensile strength or some other strength, then in different directions it will be giving different properties. For example, in this direction and in this direction they have different density and different, so along slip directions what happens, there are most packed highly packed directions, so in that direction rolling and deformation is very easier compared to these direction. So according to that, in rolling and in some other operations we choose directions according to that. So yeah, it depends. Your directions affect your mechanical properties at least. And in other, for example, in ceramics and other materials, it might affect other properties such as optical properties and other properties as well.
Yeah, actually, I recall that sir told the polycrystalline material.
Yeah,
In polycrystalline material, uh, these effects got nullified. Of like if we apply force in different directions,
yeah.
then also we will get the same tensile strength of the material for a polycrystalline material.
Yeah, because in polycrystalline materials, some of your grains will be oriented in the direction of slip direction, right? And some won't be. So uh,
Yeah, so it will nullify the effect of direction.
yeah, if we talk
So
in
in
single
mon
crystal, then it will be effective.
so if we are designing some product of monocrystalline material,
Yeah.
then what is done or how much strength or tensile strength should we consider or calculate? How can we calculate it for a monocrystalline?
For monocrystal as well, you can perform tensile testing and all.
But uh, in how many directions we perform the test?
How many directions?
Like in monocrystal material, there will be effect of this crystallographic direction.
Yeah,
If you will
so
apply different,
yeah, depending on
if
Schmidt's
you will apply,
factor, your no, tensile, your shear strength will change. Schmidt factor you have read, right? Schmidt factor is how your slip system will be aligned along the whatever the pulling direction that you are using, tensile pulling direction. So depending on that, it will keep on changing. Like in one direction, it will be so brittle that it won't deform at all, and in one direction, at a particular angle 45 or something, it will be showing a lot of ductility. So it will be changing in different direction with changing angle with the slip system.
so while designing any product, uh,
Yeah.
like how many direction do we have to consider? Or how much direction we will consider?
See, for single crystal, those are not main used much, like in industrial applications and others. So even if you are designing, you design it, for example, in some jet engine or something like that, where we use the like at higher temperatures, deal with high temperatures, then
Yeah,
we go for single
sir
crystal.
told that this steam turbine blades are
Yes,
made up of this.
yeah, then because it is dealing with high temperatures, so you want to avoid the coarsening of the crystal. Then you have to, according to like rolling direction or that, you have to consider. So, for example, you want to keep high tensile strength in particular direction. In that case, in which centrifugal force how it will be working, according to that you have to design your blades. So it will depend on application, how you want to design it, which direction there will be more force, so according to that you have to like keep the brittle part, or according to that you have to keep your ductile part. And if you are using it, for example, if you are using it in semiconductors, then you don't have to worry about your strength as much. So it will be depending on the application that you are using, and how the after designing it, how the forces will be applied, so that you have to consider your strength according to that.
Yeah, but so in conclusion, that we have to keep in mind that we have to uh, design according to different direction forces, right?
Yeah.
For a monocrystal material.
Yeah, in final application, how your stress is applied to the your component, according to that you have to keep your strength. Your strength should be higher to the whatever stress it is applying.
Yeah.
Yeah. Yes.
To ask that, like, what causes these stacking faults?
What causes stacking faults?
Yeah.
So during the manufacturing, there may be presence of the stacking faults. Like one plane is missing in some area, not entire area. Just in some area, there'll be formation. There might be formation of vacancies. Vacancy might cluster at a plane. Then that plane will be absorbed from that particular area. Then in that area, you'll be having stacking fault.
So during manufacturing of any material, a
Yeah,
stacking fault can generate by itself.
generate because of vacancies as well. So if you are, for example, you're quenching, rapid quenching, or during plastic deformation, there is formation of vacancies at particular area, then there'll be formation of stacking fault in that area.
Like intentionally, we can do it or we can't.
Yes, intentionally there can be formation because of plastic deformation. There's noted like formation of stacking faults.
So currently, I don't have any other doubts. Please check that about that doubt. I will also check about it, and if I will find something, we can discuss about it.
Yeah, we can discuss in next class
Thank you.
regarding triclinic, right?
Yeah, yeah.
Okay.
I will also check it.